Hello, welcome to my Physics 2212 Lab 2 Lines of Charge. The purpose of this lab is to determine the charge of a tape by making one tape float above another. The two main physics principles used are the electric field produced by a charge and the force that the field exerts on another charge. A brief preview of the lab is that the charge was measured to be minus 7.83 nanocoulombs using the point charge method and minus 23.3 nanocoulombs using the lines of charge method. Some of the assumptions made is that all charge is spread evenly along the tape, that both tapes have the same charge, there is no air resistance, and the tape's charges remain constant. As we can see in the diagrams, the tape is originally hanging, but after introducing another charged tape below it, it starts to float. The system consists of the charged tapes, while the surroundings are everything else, including Earth. For initial conditions, the length of the tape is 25 centimeters and its mass is 0.25 grams. After conducting the experiment, we measured that the tape begins to float when the separation distance is 1.5 centimeters, as seen in the image. Because the tape is floating in a fixed position, its net force must be zero. Therefore, the force of gravity is opposite in direction and equal in magnitude to the electric force. Previously, we used the point charge method, but now we can use lines of charge method to determine Fe more accurately. For the first part, where we calculate Fe, is to calculate the electric field at a point in the top tape. First, we study the equation for dq, which is the density times dl, which is equal to q over L times dl. Then the differential of the electric field is k times the vector times dq over r cubed, and the vector is big X minus small x, comma h, comma 0. And then finally, the electric field at the specific point is simply the integral of dE from 0 to L with respect to small x. Then we can calculate the net force at a single point, which is just the force is the charge at that point times the electric field. So using that value in, we get that the net force across the entire top tape is the integral from 0 to L of the electric field times the charge at every point. And when we solve for it, we get the formula that is in the below at the bottom. Therefore, to get the value of Q, we get from before that mg equals Fe, and then if you solve for Q in that equation, you get a value of approximately minus 23.3 nanocoulombs. For the computational model, the first and most important function is the electric field function given by a charged particle at an observation location. And first, we calculate the vector that points from the charged particle to the observation location as the observation location minus the charged particle's position. And then we simply use the formula for the electric field to calculate it, and we return that value. Then I used 30 small charges to model each tape, and the length was 0.25 instead of 0.2. That's the tape axis line. And then the dE at dq top by dq bottom is simply the electric field caused by dq bottom at the position of dq top. And finally, the arrows are built as shown in the screen. This is the results of my computational model. The yellow arrow is the force of gravity, which has the same magnitude as the white arrow, which is the electric force. The green arrows are the electric fields at every single one of the red points, which, as we can see, are correct. Some of the assumptions made by the computational model are that it treats the charge as perfectly evenly spread along the tape. It also assumes both tapes have the same charge, which may not necessarily be the case. A similarity between the experiment and computational model is that they both predict a charge of approximately minus 23.3 nanocoulombs. This is likely because they both use Coulomb's law as the underlying physics principle. The slight difference in the results could be due to the iterative approach of the computational model, which contrasts the mathematical approach of the experiment. Some sources of error lie in the fact that some of the simplifying assumptions are not correct. For instance, the charge is not concentrated in the center of the tape, nor is it spread exactly evenly along the tape. Also, the support on the hanging tape exerts a vertical force on it, but the experiments, we ignore this force. Some of the charge is also dissipated to the surroundings, and the measurements may have inaccuracies. The first additional question is what if we model the tapes as a point charge, in which case we get a value of -7.83 nanocoulombs from the previous lab. The second question is why is the estimates different? And the estimates are different by approximately a factor of 4, which comes from the fact that the line charge method spreads the charges evenly instead of concentrating them in a single point. This new method is likely more accurate because in reality the charge is in fact spread along the tape and not concentrated in one point.